Hello everyone, this is Group 1. And before I tell you what today's topic is, let me start with a quick question. Have you ever tried to send a text message in an elevator, watch it fails, and then you've seen it suddenly send a moment when the signal comes back when you step out of the elevator? I think most of us have experienced it before. At first glance, it feels like a small everyday inconvenience, but that simple situation actually captures a much deeper networking problem. So today, we'll start from the familiar experience and follow the idea all the way to communication between Earth and Mars. Our today's topic is DTN, which is delay tolerant networking. And at its core, DTN is built on a very simple idea, which is if you're cut off, hold that message and forward it when you can't send it back. Here's what we're going to cover up today. We'll begin by understanding why traditional protocol TCP/IP networking struggles under extreme delay and disruption. Then we'll introduce the core DTN idea, store, carry, and forward. From there, we're going to look at the DTN architecture, including bundle protocol and LTP. After that, we're going to discuss routing and see where it is already being used today. And we're going to introduce what we've done with our demo. Finally, we're going to look at quantitative comparisons by numbers and discuss the limitations. And we're going to wrap up things with the one key takeaway. So why does the text message sometimes fail in an elevator? The answer is that the message usually isn't lost. The moment the signal disappears, your phone just simply keeps the message locally and waits. And as soon as the connect signal comes back, the message is then transmitted. You've probably seen this similar behavior when leaving a tunnel or recovering from temporary signal outage. The message wasn't really destroyed or lost. It was simply just waiting for the opportunity to move forward. That basic idea, hold on to the data when communication is unavailable and forward it later, is exactly the principle behind the DTN. Delay tolerant networking takes this simple intuition and applies it to environments where delays and disruptions are much more severe. To appreciate why that matters, we're going to scale it up to dramatically to the space. Now scale the glitch to the Mars. An elevator cuts you off for seconds, right? And now imagine the same situation on much larger scale. Communication with the rover on Mars, which is expedition car you use on the Mars. Depending on the relative positions of Earth and Mars, a signal may take anywhere from about 3 to 22 minutes on the way. And communication links can also disappear for extended periods because planets rotate and the orbital positions changes real time. So space is just, it's not just an interesting example. It is one of the most challenging communication environments we currently deal with. And it is exactly where DTN has already been standardized and deployed. If we can solve communication across the Mars gap, then applications such as disaster recovery or remote regions, underwater, in the deep down in the ocean, those type of communications become so much easier to handle. So key challenge here is that traditional internet protocols assume there is a continuous path between the sender and the receiver. Whereas on Mars, that assumption just does not work. And that's why DTN exists. To understand DTN, we're going to follow a single bundle of traveling from Earth to Mars. We divide the journey into 5 stages. Each stage asks a question and introduces a technology that answers it. So first, why does TCP break? Second, if the connection disappears, can't we just simply hold the data? Third, if we do that, who becomes responsible for delivery? Fourth, how do we provide reliable transport when delays are measured in minutes rather than milliseconds? And finally, how do we decide where and when to forward the data? These 5 stages form the backbone of the rest of the presentation. So we're going to start with the first question. Why does TCP fail in an environment like this? Space is not simply a slower version of the internet. It violates many assumptions that TCP depends on. There are actually 4 major challenges. First, delays are extremely long and highly variable. And a round trip between Earth and Mars can range from like 6 to 40 minutes. It's very long. Second, communication links are frequently disrupted. A complete end-to-end path may not exist since it's space environment. Third, communication capacity is often asymmetric. The amount of data that can be sent in one direction may be very different from the other. And fourth, packet loss is often caused by physical phenomena such as radiation or interference rather than network congestion. What's important is that these same conditions also appear in disaster zones, underwater environment, and remote regions. So solving communication in space helps us solve many other different problems as well. Now let's see how these realities collide with TCP's assumptions. TCP relies on several assumptions that work extremely well on the modern internet. Unfortunately, each of them breaks down in deep space communication. First, TCP assumes a continuous end-to-end path. But in deep space, links may never be available at the same time. So even the 3-way handshake may never complete. Second, TCP assumes acknowledgements return quickly. But when there's delays measured in minutes, ACKs arrive too late, and congestion windows grow slowly, and link utilization becomes poor. Third, TCP treats timeouts as packet loss. But if you think about the deep space, data may not be lost at all. It just maybe simply be delayed for a long time. So TCP retransmits perfectly good data and wastes bandwidth. Finally, TCP interprets loss as congestion. But a lost packet in space may be caused by radiation rather than network overload, and TCP slows down even when slowing down is unnecessary. The takeaway is not that TCP needs to be improved. The problem is that its underlying assumptions no longer match, which is, we're talking about the space environment, right? So instead of modifying TCP, we came up with DTN, and DTN starts from a different premise altogether. The different premise begins with a surprisingly simple idea. Like I said before, if communication is unavailable, don't just throw the data away, don't discard it, keep it, and wait. Then forward when communication becomes possible. This is the store, carry, forward model. It's exactly what your phone does in an elevator. The message is stored locally, carried through disruption, and forwarded once connectivity comes back. But this immediately raises another question. If a node is storing the data and that node fails, who becomes responsible for delivery? Who's delivering those data? DTN's traditional answer is custody transfer. A node formally accepts responsibility for delivering the bundle and then passes that responsibility to another node later. A useful analogy is a parcel delivery system. Once the next depot signs for a package, responsibility moves to that depot. That transfer of responsibility is what distinguishes DTN from just simple caching. The data is not merely stored, but it's more actively managed and forwarded through the network. So where do these ideas actually live? DTN does not replace existing networks. Instead, it adds additional layer above them. It's called bundle layer. The unit of communication becomes a bundle rather than a packet. Bundlers can move across different underlying networks using whatever transport technology is, and must appropriate for each segment. For example, TCP may be used on terrestrial side, while a different protocol may be used on deep space link. And this flexibility allows DTN to operate across highly heterogeneous environment. And the current standard for this architecture is Bundled Protocol version 7. So people call it BPv7 in usual. And one detail worth noticing is that deep space segment often uses a transport protocol called LTP. So we're going to talk about why that protocol exists. Because TCP struggles under extreme delay, DTN relies on a different transport protocol for deep space communication. And that protocol is LTP. It's called Link Lighter Transmission Protocol. LTP introduces two important ideas. The first one is distinction between write data and grain data. Write data must arrive reliably. Grain data can be treated as a best effort. The second idea is deferred acknowledgements. Instead of expecting ACKs to arrive quickly, LTP is designed around the reality of very large round-trip delays. As a result, reliable transport remains possible even when delays are measured in minutes. Simply, like even when the delays are very long, it still remains possible. Together, these features make LTP much better suited to deep space links than traditional TCP. At this point, we've covered 4 of our 5 stages. So let's briefly put them together before moving to routing. So here's a small recap about what we've talked so far. The assumptions of a continuous path breaks down. Like simply just doesn't work in the space environment. So we came up with the store and carry. Store and carry forward removes the need for the path to exist right now. And custody transfer ensures responsibility moves forward and through the network. LTP provides reliable transport across extremely delayed links. So the result is that data can eventually reach its destination even when a complete end-to-end path never exists at the single moment in time. And that's the central idea behind the DTN. And lastly, there is only one question remaining. If we don't always have a path to the destination, how do we decide where to send the data and when to send it? So that brings us to routing. The final stage is routing. In traditional networks, routing protocols generally assume that links are available right now. DTN cannot make that assumption. Instead, routing depends heavily on how predictable the environment is. Let's start with the space. The movement of planets, satellites, and spacecraft is highly predictable. We can just calculate like orbital positions like far in advance. We can expect it. Because of that, DTN can use a routing method called contact graph routing, or CGR. CGR uses a contact plan, which is essentially a schedule describing when communication opportunities will become available. Instead of asking, where can I send this packet right now? CGR just asks what communication opportunities will exist in the future. So where, like what I could talk in the future, if that makes sense. That works very well in environments where connectivity can be predicted. But not every DTN environment is so organized like this. Consider a disaster area where infrastructures has been damaged and mobile devices are moving unpredictably. In that situation, future contacts cannot be calculated in advance. Instead, DTN relies on opportunistic routing. Nodes simply just forward bundles whenever the forwarding opportunity appears. So different strategies exist. Epidemic routing forwards copies very aggressively to maximize delivery probability, but at the same time, this creates substantial overhead. Spray and wait limits it limits the number of copies, trading some delivery performance for much better efficiency. The important point is that DTN can operate in both predictable and unpredictable environments. And the predictable side of DTN is already being used in real missions today. At this point, it's worth emphasizing something important. DTN is not just research concept in our theory. It has already been deployed and it has been tested in the real-world space systems. One early milestone was that DNet experiment in 2008, which demonstrated DTN communication in space. Today, NASA's ION implementation operates on the International Space Station. Looking ahead, future lunar communication infrastructures such as LunaNet are also being designed around DTN principles. What's interesting is that technology development for the most extreme communication environment eventually becomes useful back on Earth. The same ideas appear in the disaster response networks, remote sensing systems, underwater communication, and other highly disrupted environments. In other words, solving the hardest case first creates solutions that can be applied much more broadly to other situations. So that's the theory and the real-world deployment. Now we're going to talk about what our team actually did. Up to this point, we've discussed DTN conceptually. We wanted to take the next step and verify these ideas ourselves. To do that, we used ION-DTN, which is NASA JPL's open source implementation of DTN. You can find the source in the GitHub page down here. And this is not just simplified classroom simulation. It was the same software family used in real DTN deployments. So our goal was straightforward. Could we reproduce the core DTN behavior on ordinary laptop like we have on the desk? To answer that question, we used ION's built-in delay simulator. It's called owltsim to create the Mars style communication delay. Then we transmitted the bundle across the disrupted lake and observed how the system behaved. Most importantly, we recorded the execution logs, so the experiment remains reproducible even without the live demonstration. So let's first look at the setup. So the experiment itself is very simple. On the left, we have the sender, we call Earth. On the right, we have the receiver that we call Mars. Between them, owltsim introduces a one-way delay of, let's say, 600 seconds here. And that means a receiver cannot hear anything from the sender for the first 10 minutes. At time 0, we submit the bundle containing the message, "Hello, Mars." At that moment, communication is effectively unavailable. The bundle therefore cannot be delivered immediately. Instead, ION stores the bundle locally and waits for communication to become possible, and then forwards, basically send. And this setup represents the smallest experiment that still demonstrates the essential DTN behavior. The key idea is simple: store, hold on to it, and when you can send it, then you forward. Now let's discuss exactly what owltsim does and does not simulate. So before looking at the results, important question naturally arises. How realistic is owltsim? The answer is the owltsim accurately models the time. And when we configure a 600 seconds delay, every transmission is delayed by exactly that amount. It can also represent links becoming unavailable and after later returning. However, owltsim does not simulate the underlying radio physics. It does not model antennas, RF propagation, and atmospheric effects or radiation-induced bit errors. So it doesn't simulate every single stuff, so it's not complete deep space communication simulator, and that's an important distinction to make. What gives the experiment credibility is that the core DTN mechanisms themselves are not simulated. Store, carry forward, bundle handling, and custody processing are all performed in ION's actual implementation. So owltsim we used in our demo simply just supplies the delay. And the networking behavior comes from real DTN software. With that distinction established, let's look at the experiment. Here's what happened during the experiment. I kind of colored with the red and blue so that you guys can check it easily. And first, we started the receiving application. Then we sent the bundle from the transmitting side. The order matters because the receiver needs to be ready before delivery occurs. At time 0, the sender generates the bundle. Because the communication is unavailable, the bundle cannot move forward immediately. Instead, it's just stored locally. If we were just to rely on the traditional TCP, this is exactly the point where connection would fail because it has nowhere to send the message. But DTN behaves differently. The bundle remains stored while waiting for the future communication opportunity. Then, if you look at the third line, 600 seconds later, once the configured delay has elapsed, the bundle is forwarded and successfully delivered. The receiving side obtains the message "Hello Mars," and custody acceptance is confirmed there. You can check on the screen. This demonstrates the central DTN premise. The communication path does not need to exist right now. You just have to store it, wait, and if you can send it, then you can send. It only needs to exist eventually. Now, let's quantify the difference. For this example, we assume a one-way delay of 12 minutes. That's roughly middle value within the Earth-Mars communication range. A 12-minute one-way delay corresponds to 24 minutes round trip. And now consider TCP. Before any useful data can be exchanged, TCP requires a three-way handshake, as you know already. That process takes approximately 1.5 round trips. And with 24-minute RTT, connection establishment alone takes about 36 minutes. And that's assuming nothing goes wrong. If connectivity disappears during the process, TCP must restart and eventually times out. Whereas DTN approaches the problem differently. Rather than just waiting for the complete end-to-end path, it stores the data and delivers it later when communication becomes available. That's why describing DTN as faster would be kind of misleading. And DTN succeeds because it is built on different assumptions about how communications work. Another way to understand the challenge is through the bandwidth delay product, or BDP. BDP is simply bandwidth multiplied by round-trip delay. Suppose we have 1 megabyte per second link and 24-minute round-trip time. The result is approximately 180 megabytes of data in fleet at once. That's big amount of unacknowledged data. And TCP struggles because ACKs arrive so slowly. The sender cannot efficiently keep the communication pipe full. And when you look at the DTN, DTN largely just avoid this problem. Rather than treating the entire path as one continuous connection, DTN stores and forwards the data one hop at a time. As a result, it does not depend on maintaining massive amount of in-flight data across the entire end-to-end path. Even the throughput mathematics points towards the same conclusion. At this point, it's important to discuss DTN's limitations. DTN is not universal replacement for TCP and IP, and intermediate nodes may need to store data for long periods of time, and this can create significant storage requirements. And congestion control is also less mature than in the traditional internet protocols like TCP/IP. And because delivery may occur much later, like later, so DTN is generally unsuitable for applications that require immediate interactions. So the decision rule is just very simple. If communication paths are frequently disrupted and long delays are unavoidable, DTN is often the right solution. And let's say the connectivity is stable and latency is low. Traditional TCP and IP remains the best or better choice. Understanding where DTN loses is just as important as understanding where it wins. And before concluding, we're going to talk about what our demonstration validated from what it did or not. What we successfully demonstrated is that a bundle can move through all 5 DTN stages. We showed store carry forward behavior using NASA's ION-DTN, a GitHub source. We verified successful delivery despite communication disruption. It can work in the disruption. And we illustrated the difference between TCP and DTN under these conditions. At the same time, our project has limitations still. The setup involved only 2 nodes. The delay was simulated rather than generated by a real deep space communications channel, but we just used the simulator. And owltsim models, it models timing, it models the time. It simulates the delay, but it doesn't simulate the radio physics. And we did not evaluate large-scale routing, security mechanisms, or network-wide performance. In short, I could say we validated the core DTN mechanisms, not the entire operational ecosystem. So if there is one idea to remember from our team's presentation, it's this. Traditional networking assumes a path exists now, but DTN assumes a path that will open someday. And that single difference changes everything. Instead of requiring continuous connectivity, DTN allows communication to survive delays, disruptions, and temporary disconnections. So we begin with the simple text message stuck inside an elevator. Then we followed the same idea all the way to ION. Along the way, examined the challenges, the protocols, and routing strategies, and finally, we verified the concepts using NASA's software. The next time a message is delayed, and so it suddenly arrives after losing a signal, remember that the same principle is helping make communications across the solar system. And thank you. I'll be very happy to take any questions. You guys can leave the questions in the QA board. And this is our sources, the references we used throughout this presentation. And thank you for listening.